Hi, everybody. Welcome back to General Science. Today, we're going to talk about one of the forces that you've interacted with the most, probably in your lifetime, without really even realizing it, which is gravity. Gravity is the force that holds objects of mass together. So basically, what that means is anything with a large amount of mass can exert this force called gravity. And when I say a large amount of mass, I'm talking about the kind of mass of planets and moons, um, and stars, right? They're the ones that exert the most gravity. But everything, all matter exerts gravity, just in smaller proportions, right? The less mass, the less gravity. The more mass, the more gravity. So that technically means that everybody has their own gravity field. It's just very, very weak. Okay? Now, big celestial bodies like I said, planets and stars and moons, right? They're very, very large. They have tons of mass, and so they are able to exert a much stronger gravitational field. That means that things that get close enough to them are going to be acted upon by that gravitational force and pulled towards those objects. That's why when you're on the Earth and you jump up, you always come back down, because the Earth is exerting that gravitational force on you. You're able to exert a force to push yourself off the Earth, but you can't keep generating that force for long enough to keep yourself floating in the air. So you fall back down and you land on the ground. Now, in the world of classical physics, they didn't really understand why that was. Now, recently, right, and more in a modern physics type of thing, in the last, several decades, we've come to realize more and more about why gravity works the way it does. And I'm not really familiar enough with that information to teach it to you today. Okay? But what I can tell you is that in the classical era of physics, they really ended up figuring out how gravity worked on Earth, right? We weren't able to leave the planet, and so they really focused on what this force was on our planet. The first person to really kind of piece this all together and put some math behind it was Isaac Newton, and he figured out a few things about gravity. The first of which is that it was a force, right, that interacted between two objects. The other thing that he figured out was exactly how quickly the Earth can pull things back down to itself. Now, the accepted number for the acceleration due to gravity on Earth is 9.8 meters per second squared. And if you're in a high school physics course, you're going to need to know that number. It's one of the things you're just going to have to memorize. 9.8 meters per second squared. That's the acceleration due to gravity on Earth. Now, if you were to go to a different planet, that acceleration would change, right? The moon, right, has a third of the gravity of Earth. So that means the acceleration due to gravity on the moon would be roughly a third of that of Earth. Now, Jupiter is about twice as big as Earth. And so that means its acceleration due to gravity would be two and a half-ish times bigger, right? So the more mass, right, Jupiter is much more massive, the more gravity. The last thing that we've been able to figure out in classic physics is how the different planets interacted with each other, and they wrote a special equation for it. Basically, it's the difference between what physicists call big G and little g. Little g is the acceleration due to gravity on Earth, right? Little g equals 9.8 meters per second squared. Big G, however, is the gravitational force between two large objects. That equation is the force of gravity is equal to the gravitational constant, big G, which is just a number that makes the math work out, times the two masses divided by the distance in between those things squared. That equation basically just shows what the force of gravity is between two much larger objects, that it's not dealing just with Earth's gravity and a small object, right? The little g is always 9.8 because there's never anything large enough to exert its own gravitational force on the Earth. That's, in our general purview. So it just ends up being 9.8 meters per second squared. The other equation is for two larger objects, like let's say the Earth and the Moon. Right, those two are very large celestial bodies. They have large masses, and so that equation applies to that sort of situation instead of a much smaller, simple situation, like an apple falling on Newton's head. Anyways, that's what we've got to do to talk about gravity. Next, we'll talk about some more interesting things physics-wise. And then finally, when we're done with our physics part, we'll move on to our final science of general science. I hope you're as excited as I am. See you soon.